I'm Zhang. Today I'm going to present our work, BunnyHop exploiting the instruction prefetcher. It's a joint work with Mingtian, Sioli, Chitchanok, Daniel, and Yuval. So before I start introducing our work, I will firstly say two fun facts about our work. So the name of BunnyHop is actually, so our paper is called BunnyHop, and it is published in the year of Chinese Bunny Year. And the second fun fact is that I also born in the year of the Bunny Year. So I think it's very interesting. So in our work, we study how the instruction prefetcher works on the Intel processor, and we found that it not only improves the performance, but it also brings new security vulnerabilities. So our modern processors are very fast, but memory access are very slow. So however, for the processor to execute instructions, they need to firstly be brought from the memory, and we don't like the slow memory access. So one of the ways to solve this issue is that we bring instructions as early as possible to the processor. And this job is taken by the instruction prefetcher on the modern processors. So now I will show how the instruction prefetcher works with an example. So the code on the left side doesn't matter what actually it does, because we just want to show how the instruction prefetcher works. And in fact, instruction prefetcher also doesn't know what instruction it is prefetching, because it only checks the virtual addresses. So for example, when the NOP instruction is being executed, the instruction prefetcher will not just wait there, and instead it will bring instructions ahead of the time to the processor. And these instructions will be further stored in a structure called cache. So accessing instructions from the cache is much faster than accessing them from the memory. So with all these instruction cached, the processor can execute these instructions very fast. It works well. However, we have a problem when the processor is executing branching instructions, because we have two possible targets here. So the instruction prefetch at this stage does not know that there is a branching instructions, and it may potentially prefetching instructions on a path that will not be executed. And it is harmful to the performance, and we wanted to avoid such situation. So in reality, the instruction prefetcher relies on a structure called the branch predictor. So the branch predictor will store the execution histories of all the branches and predict an outcome of a branch. So the instruction prefetcher will fetch an instruction and ask the branch predictor whether there is a branch exists here or not. The branch predictor will then do a search in its histories and respond it with possible target addresses. So for example, in this case, if the branch predictor has such an record says that previously this branch is taken, so it will tell the instruction prefetcher you need to fetch the target address. The instruction prefetcher will then follow the instructions from the branch predictor and start bringing the addresses from the target address and also instructions beyond the target addresses to the processor. And they will be stored in, and they will be cached. So instruction prefetcher is good, branch predictor is good, cache is also good. The good things are always shared between processes, and as an attacker, we like shared resources. So as an attacker, we can ask the instruction prefetcher to check an address for us. So we can ask the instruction prefetcher to check whether there is a branch at an address or not. So what an attacker can do is an attacker can create a NOP instruction that has the same address as the conditional jump in the other process, and ask the instruction and execute this instruction. So the instruction prefetcher will now start prefetching instructions and ask the branch predictor whether there is a branch here or not. In this case, the branch predictor will respond a target address because previously the conditional branch is taken, and the instruction prefetcher will then bring the target address in the attacker memory to the processor. And this target address will also be stored in a cache. Now an attacker can perform a cache attack to learn whether such a target address is stored in the cache or not. And we know very well about cache attacks, so we have plenty of cache attacks there, and they are very easy to perform and they are very reliable. So if we consider the branch predictor as a bunny, that branch predictor state as a bunny, and we found that with instruction prefetcher, this bunny can actually be converted into the cache, which becomes a cache state that allows an attacker to observe with cache attacks. So here we see the BunnyHops, and we have the main technique or the main observation we have in our paper is that we can translate the branch predictor state into a cache state with the help of instruction prefetcher. So BunnyHop attack is very nice, and with such a nice technique, what we do is we firstly reverse engineering how the instruction prefetcher works on the Intel processor. And furthermore, we do a bit more reverse engineering on the branch target buffer. And for the first time, we show the replacement policy of the branch target buffer on various Intel processors. And furthermore, more interestingly, we found that the branch target buffer on the Intel processor actually contains two types of branches, which is called the long branch and short branch. Based on our reverse engineering result, we performed three cool attacks. So in the first two attacks, we applied the techniques from cache attacks on the branch predictor. So with Flush+Reload technique, we are able to learn the branch predictor state happens on the same hyperthread. And then with the Prime+Probe technique, an attacker can learn the branch predictor state crossing hyperthreads. And in the end, we propose an attack called self-eviction. It is a variant of evict time attack. And with self-eviction, we can confuse the victim to evict its own data. So in the self-eviction, we use the branch predictor in a very different way than previous attacks. In the rest of the talk, I will explain how the self-eviction works. And if you have interest in the results of our work, you are welcome to read our paper. So self-eviction is a variant of evict time attack. So the first job of it is to evict secret dependent data from the cache. That's how the evict time attack works. So assume that we have a secret data that's stored in the cache, and to remove the data from the cache, it is simple. So an attacker just needs to access a bunch of memories, then that can evict the secret dependent data. So in the past years, research we know that evict time is very powerful because it is easy to evict secret dependent data, and we could then just measure the execution time of the victim process. We can infer secret dependent behaviors. So to mitigate such an attack, we have cache coloring technique. So what cache coloring does is it will assign different cache sets to different processes. So each process will only get his own specific cache sets. And in this case, an attacker process cannot access this colored cache which belongs to the victim. So an attacker cannot evict a victim's data anymore, and the evict time attack is actually defeated by the cache coloring technique. However, on the other side, although the attacker cannot evict memories, the victim can evict its own memories. So the victim's memories can actually be accessed, and they can actually be used to evict its own data. However, there will be however, it will not be performed automatically. And what we can do is we can point in the branch predictor to tell the instruction prefetcher to actively fetch these memory addresses that will evict victim's data before the victim is actually using them. So what we do is we can execute a chain of branching instructions. So what happens here is that the branch target addresses will contain another branch that branch to another branch target addresses. And just by simply executing this chain of branches, the branch predictor will be poisoned. And the branch predictor will remember how the branching instructions performs in the past. And when the victim process is being executed, the branch predictor will tell the victim process where to prefetch the memories. And therefore, the victims will actively prefetch all of these the memories that will be used to evict the victims the secret dependent data. And now what we lack here is we lack a trigger that can trick the instruction prefetcher to start doing prefetching. So here we only need an instructions in the victim process, and it can be any instruction because the instruction prefetcher does not care what it is prefetching. And this instruction just need to be executed and just need to be prefetched before the secret dependent data is actually used by the victim process. So after the victim secret dependent data is evicted by its own memory, and the attacker just need to measure the execution time of the victim process. So if the process takes longer time, it means that the secret dependent data is re-accessed from the memory by the victim. Otherwise, it will be much faster because the victim doesn't need to fetch them from the memory. So in our paper, we present a proof of a concept attack on the protected AES, which is running in the Linux, which is running in the kernel. So we show that with less than 20,000 traces, we can successfully recover one key byte. So it cannot be done with evict time attack if your cache is cache colored. So in summary, in our work, we present a BunnyHop technique which can translate the branch predictor state to a cache state. And based on this technique, we perform 2 reverse engineering work on the instruction prefetch and the branch target buffer. And in the end, we apply the cache attacks on the branch predictor, and we perform 3 interesting attacks on the branch predictor. If you have interest in our work, you are welcome to read our paper, and our code is open source, which is available on the GitHub. And thanks for the listening. And I know it's the last talk in the last session on the last day, so very thanks for being here with me. Thanks.